Here we'll talk about the base-promoted hydrolysis, in this case of esters, or the saponification reaction process. And this process forms molecules that we use in soaps. So we'll talk about the properties of those molecules as well. For this reaction, to form a soap, we'll start with a fat or oil molecule. So that means that this molecule will have a long carbon chain. Now I'm just going to represent that as an R group. And we'll have a ester with a methyl group bonded to that oxygen. But we start with a fat or oil molecule. Which means this R group is a long chain. I'll show you a specific example in a little bit. So if a molecule such as this is exposed to a strong base like sodium hydroxide, then this reaction, although reversible, will form what we call a carboxylate carboxylate salt, where this oxygen, instead of being bonded to a methyl group, is just negatively charged. So it's an ion. This is ionic compound or ionic molecule. So this is a carboxylate salt. Salt because we have both O-, we have an anion, and then sodium as a counter ion is present as well. And this is the general structure of soap molecules. Byproduct is methanol, so the carbon chain that was part of the ester. So let's do some highlighting here. This OCH3 is now present in the alcohol byproduct, and then the oxygen from the OH group is present in the molecule, this O-. And then we'll use green. This hydrogen from the OH is part of that alcohol as well. And then everything else was that original fat or oil molecule. Now you might imagine if we added acid, now this wouldn't result in the soap molecule, but we could add acid to produce the carboxylic acid. Something like HCl, now it's a strong acid, that will certainly protonate the carboxylate salt, and you would form the carboxylic acid version. So this carboxylate salt is really just the conjugate base of the carboxylic acid. So this is the ingredient or the functional group present in many soap molecules. So let's draw out the mechanism. Again, we're going to use an R just to represent that long carbon chain, and I'll show you an example of this after the mechanism. We'll use still that OCH3 group for the ester. And then when we're in the presence of a strong base like hydroxide, that negatively charged oxygen is a strong enough nucleophile to directly add to the carbonyl carbon. So there is no acid present, so we're not activating the carbonyl by protonating the oxygen, since this is in basic solution. So really what we're doing here is immediately doing nucleophilic addition to add that OH group to the carbonyl. So we form a tetrahedral intermediate. R group bonded to carbon, bonded to the OCH3 group. We have a single bond to the oxygen and a single bond to the OH group. Now in this next step, to promote the forward reaction to produce our carboxylate salt, we have this negatively charged oxygen, and that will kick off that methoxy group. So it will recreate a double bond between the oxygen and the carbon, and the OCH3 group will leave as an ion. Now it's okay to leave as an ion here because again, we're not in acidic solution, so nothing's getting protonated before it could exist as a negative ion, as an anion. And if we think about this carbon that's bonded to 3 oxygens here, that carbon is bonded to 3 electronegative groups. It's lacking electrons in a major way. So that negatively charged oxygen is going to share its electrons to create an overall more stable molecule. So our anion now that will generate, I have to kind of angle downward here. So the anion that will generate is the OCH3 anion, and then our molecule is a carboxylic acid, and we form this OCH3. That's what has left the molecule, that second purple arrow has shown. So this step, the second step, is elimination. We've eliminated the OCH3, the methoxy group. And then now we have, let's emphasize this OH bond here. That will come into play in this step of the reaction. We have a carboxylic acid, slightly acidic. pKa is about 4.8. And we have a negatively charged oxygen present. So this last step is a proton transfer reaction. Got ahead of myself. We need to draw these arrows. So the methoxy group, negatively charged oxygen, will take a proton from this carboxylic acid, and that causes that carboxylic acid oxygen to become negatively charged. So we have our carboxylate, the soap, and we have CH3OH. CH3OH in this last reaction, which is a proton transfer reaction. The pKa of acetic, or not acetic acid, but of our carboxylic acid is about 4.8. The pKa of methanol is about 15. So the carboxylic acid is a much stronger acid, so this reaction lies towards the products, the carboxylate salt and the methanol alcohol. Now we haven't been drawing the sodium ion, but let's remember we have sodium hydroxide present, so that is a counter ion. In each step, wherever that negative charge is, it's countered by sodium. So our final product, the sodium and the carboxylate anion, form our carboxylate salt. So there's a reaction to go from an ester to the carboxylate salt. Now here's an example, a real example of the carboxylate salt as a soap, so something that you might see present in the ingredients list of your soap. And this is, of course, we have the carboxylate salt part of the molecule. And if this carboxylic or carboxylate salt carbon is then bonded to, we're not going to, well, we will draw it out, but for now let's draw the formula. 16 CH2 groups and then a CH3. This is sodium stearate. If we actually draw out, we'll do the skeletal structure for this. We have 18 carbons total in the molecule. So here's 2, 3, 4, 5. There we go. There's 18 carbons. On our last carbon, we have that functional group. Now with this molecule having that long carbon chain, remember if we have a long carbon chain without any polar bonds, polar or electronegative atoms, this is a hydrophobic part of the molecule. So it's not polar, it only, in this part of the molecule, only London dispersion forces are present. So hydrophobic molecules or hydrophobic chains mix well with oils, greases, etc. So that part of the molecule that's hydrophobic will mix well with oils and greases. Now, the right side of how we've drawn it here, this right side of the molecule, we have polar bonds and we have formal charges. We have a negatively charged oxygen and a positively charged sodium. So this part of the molecule is hydrophilic. So this does mix well with water. Remember, water, very polar molecule. Hydrogen bonding capability. So if we have a polar end, this polar end of the molecule is hydrophilic, it will mix well with water. We also have a hydrophobic part of the molecule. And so in total, this entire molecule having both sections, a hydrophilic section and a hydrophobic section, allows hydrophobic materials, so the whole thing, hydrophobic materials like oils and grease they'll interact with the hydrophobic part of the molecule, but then we also have this hydrophilic part that can mix well with water. And so that allows these hydrophobic materials, if you imagine you're trying to clean a plate or clean yourself, if you have oily hair, you're washing your hair, the hydrophobic part of the material of this carboxylic salt mixes with the oils, and then the hydrophilic part mixes with the water, so that allows the oils and greases to be washed away with water. So here, let's see if this works. I've got a picture of the back of a Dove cleansing bar. So if we look at the ingredients here, the first ingredient is a sodium, and then another molecule that ends with an 8. So here's an 8, sodium something 8. We have stearic acid, so that's carboxylic acid version. Lauric acid is a carboxylic acid. Sodium tallowate is a carboxylate salt. You'll see a few more, and then right here we have sodium stearate. So that's that molecule that we had drawn with the 18 carbons. So these types of molecules are common in soap because of the properties that they have. Now you may have also heard of micelles. I have an image of that over here. So let me carry this over. If you have a high concentration of these carboxylate ions in solution, then the nonpolar tails, which are the hydrophobic area of the molecule, the nonpolar tails would kind of gather together, and those are represented by these wiggly lines. They gather together, they are attracted by London dispersion forces to each other, and then the polar head group for a carboxylate ion, so that negatively charged oxygen, is represented by the circle here. That negatively charged oxygen interacts with water, and so those will form the outside of this cell. So this is a micelle, where the inner parts of the cell are the nonpolar chains interacting with each other through London dispersion forces, and the outer part of the cell are where the ions are, which interact with water.